Historians are very interested in counting coins. Coins are the most durable form of monetary representation in the ancient world. Not the most important, there were lots of other forms of money which tend not to survive, but coins are the most durable. And as such, it seems logical that counting them might allow us to understand how much money there was, which is potentially very significant for economic history. There are lots of ways you can do this, and I've talked about those before. But in short, most people agree that the best results, where it is possible, are achieved by undertaking die studies. And last week I uploaded a paper online I wrote in 2015 for the last International Numismatic Congress, which is a big multi-stranded event that happens every 6 years. That paper was about one particular aspect of counting coins, the Workstation Problem, which is interesting because it combines historical and mathematical theories. Specifically, a type of maths called graph theory, and I will explain that in a second. But first, a little bit about how coins are made. Ancient coins derive from 3 independent traditions, usually referred to as the Lydian, Indian, and Chinese, each of which used a different method of manufacture. The Lydian tradition employed a method called die striking, in which a blank piece of metal was placed between 2 dies and the whole arrangement struck with a hammer to impress the design. The dies that are used have a negative version of the coin design. The upper die, called the reverse, takes the hammer blow and impresses the back of the coin, and the lower die, called the obverse, sits underneath and impresses the front of the coin. Because each die had to be hand engraved, you can look at a coin and tell immediately if it was made using the same die as another coin. And that means you can count the number of tools. If you assume that counting the number of tools indicates the number of coins that were made, and that the number of coins indicates the amount of money, then you get to some interesting numbers for economic history. And yes, there are a whole bunch of assumptions in there, any of which could be the focus of an entire lecture. But I'm going to skip over them because the point today is that simply counting the number of coins is not the whole story. Tony Hackens was a French archaeologist, and he was one of the first people to point out that knowing how many coins were made is not the same as knowing how quickly they were made. To illustrate this, let's think about one of the subjects he was interested in: classical Greek coins. Athens in the 5th century BC made one of the most prolific coinages in the ancient world. So large, serious doubts have been expressed as whether or not you can in fact do a die study of it. Yet the building that was used to make this coinage was tiny. It was probably the smallest state building in the city, because even just 2 people working in relatively short shifts can produce thousands of coins, and under that kind of pressure, ancient dies would break or wear out very quickly, possibly in just a few days. Yet despite this, many ancient states used the same dies not for weeks or months, but for years. And the only reasonable conclusion we can draw is that most of the time, most mints were not making coins. Hackens wondered what that meant for the rhythm of production. Did the mint work part-time and steadily produce a certain number of coins every week? Or did it make one huge batch in an intensive period of production and then shut down completely for a long period? Obviously, the answer to that question is going to be different for different mints, and at different times at the same mint. One way of working out what is going on is to look at the number of people making coins. If the mint is making coins at a steady rate, it can employ the same people and they just work longer. But if the mint suddenly employs a large number of people all operating parallel workstations, it's pretty good evidence of an intense period of production. And that's why workstations, or counting them, matters. We'll come to the problem bit in a moment. How can we possibly tell how many teams of people were making coins? Thousands of years ago, when in most cases no administrative records survive. Okay, let's start with a simplified description of 2 people making coins. They have one obverse die fixed in an anvil, and one of them holds a reverse die, while the other one swings the hammer. Each coin they make like this will be struck by the same obverse and the same reverse die. Numismatists depict this in diagrams by using different shapes or colours and connecting them with a line, indicating that we know that this obverse was used with that reverse. It doesn't matter how many coins are involved, whether that link is testified by one coin or thousands, and that makes the diagrams really useful for looking past the coins themselves to the production behind them. If those workmen break a die, and the reverse die tends to break more quickly because it takes the hammer blow, then they will replace it, and our diagram will now have 3 dies in it, with both reverses being connected with the same obverse. If there is enough data and the mint keeps making coins and replacing dies, our diagram ends up looking like a chain. And this is not just theoretical. Lots of studies of ancient coins have demonstrated that this kind of pattern is seen at actual mints. Now, if a mint sets up 2 workstations but gives each workstation its own pair of obverse and reverse dies, we wouldn't be able to tell that the 2 stations were operating together. Fortunately for us, that does not seem to be how ancient mints operated. When there is more than one workstation, ancient mints seem to have used what we call a die box system. Imagine that each workstation has an obverse die fixed in it, but the reverse dies are all kept together. When a team starts work, they grab a random reverse and take it to their workstation. On a different shift, that reverse might get taken to another workstation, and in principle, the mint might make coins pairing all the different obverses and reverses, so they would all be connected in our diagram. The resulting diagram looks very different, which is intuitively obvious. But exactly what is it about the diagram that tells you that it represents 1, 2, 3 or more workstations? And that is the workstation problem. How do we reconstruct the way production was organised from the data about obverse and reverse pairings the coins provide? It's not a problem historians have completely solved, but there has been progress in the last 10 years, and some of it depended on borrowing tools from a branch of mathematics called graph theory. You see, these diagrams that numismatists make, connecting shapes with lines to represent the dies, are known as graphs in mathematics. Mathematicians call the shapes nodes and the lines edges. And they've spent a lot longer thinking about this problem than numismatists have. So it turns out you can make progress if you borrow some of those mathematical concepts. And I am going to talk about 3 of them: isomorphism, colour, and planarity. Isomorphism means that 2 things which look different are really the same shape. In the case of a graph, you can move the nodes around as much as you like and make the edges longer or shorter, but as long as the connections remain the same, it is the same graph. That's important because it shows us we can rearrange our data in a variety of ways, which may mean different things to a historian. And it means that if you demonstrate that something is true by arranging the graph in one way, you've demonstrated it's true for that graph regardless of how you arrange it, because all the different arrangements are isomorphic. They all represent the same thing. The second concept is colour. Colour is a property of a graph, one of the things that does not change no matter how you arrange it. Imagine that you painted each node on the graph, but the no 2 connecting nodes were the same colour. What is the minimum number of colours you would need for any particular graph? For this graph, which is called K5, you need 5 different colours, so it is a 5-colour graph, which immediately tells us it is of no interest to numismatics, because any diagram depicting ancient coins would have to be a 2-colour graph. Why? Well, we've already mentioned this. The obverse and reverse die do different jobs. They are usually different shapes, and the obverse is always paired with a reverse. So you can think of the obverses as all 1 colour, and all of the reverses as a 2nd colour. Which brings us to planarity. Mathematicians call a graph planar if there is some way to arrange it in which none of the edges connecting the nodes cross. This particular graph, which is called the utility graph, is not planar. There is literally no way on a piece of paper of drawing it without the lines crossing. And this graph is special, both in graph theory and in die studies. It's special in graph theory because all non-planar graphs must in a sense contain this or the K5 graph. And of those two graphs, only this one is two-coloured. In die studies, it is special because it's what, in theory, 3 workstations sharing a die box with 3 reverse dies would look like. Since it is possible to demonstrate formally that a graph is non-planar, it is therefore possible to demonstrate that a die chart represents a more intense production featuring 3 or more workstations. This was done for the first time in 2009 with coins minted in Afghanistan by the Kushan king Bhima Kadphizis, which showed that far from previous assumptions that the coins had been evenly distributed across his reign, that they were in fact produced very sporadically and that the vast majority were concentrated in a very short period of time. Since then, other non-planar die charts have been found, and they are increasingly giving us a sense of when mints made coins intensely and when they did so at a relaxed pace. There is still a lot more to do on this. The paper I put online discussed some of the ways we could try to make sense of these charts, but it also left a lot of open questions. The next International Numismatic Congress was due to take place in Warsaw next year, and I was kind of looking forward to seeing whether or not anybody had expanded on the subject. Unfortunately, the COVID-19 outbreak has been particularly disruptive to academic conferences, and this one has been postponed until 2022. So I'm going to need to show a little bit more patience.